In this video, I'm going to express the position and momentum operators in terms of the ladder operators. Then I'm going to take those definitions for position and momentum and substitute them into the Hamiltonian for the quantum harmonic oscillator. Let's get started with A and A dagger. These are the ladder operators. I wrote these definitions down in the previous video in the quantum mechanics playlist. So the only difference between A and A dagger is a minus sign. These guys are both combinations of position and momentum. There is an imaginary unit I over here. So when we take the Hermitian adjoint, which is denoted by this dagger at the top, we have to change I to minus I. So that's the same as the process of complex conjugation. So we're just taking the complex conjugate over here. Position and momentum are not affected by this Hermitian adjoint. So if we take a dagger and we put it up over here, these guys are actually equal to their own Hermitian adjoint. That's because these are Hermitian operators. Position and momentum are Hermitian operators, and that means they actually correspond to real observables. So you can get observable values in the real world from these operators. And their eigenvalues are the possible values that these operators can have. So now let's do some manipulations between these guys, and we can actually write the position and the momentum in terms of A and A dagger. First, I'm going to take A dagger, and I'm going to add to that A. So I'll do that underneath. I'm going to take A dagger, I'm going to add to that A. So keep in mind, this is a dagger in the top, and this is a plus sign. So they're sometimes a little confusing when you're writing them by hand. We also have these little hats on top to denote the operators. So if it has a hat, it's an operator in quantum mechanics. So what's going to happen if I add these two expressions to each other? Well, both of them share this common factor at the front. So I'm just going to write that common factor over here. We're going to have m omega over 2h bar. That's the common factor. But what are we going to get from the inside of these brackets? Well, this momentum term has a plus sign, and this momentum term has a minus sign. So we're going to have minus plus. Those guys are going to cancel each other out. But this position operator is not going to cancel itself out. So we're going to have two copies. We're going to have this plus this. So that's going to give us 2 times x hat. And we can actually move this 2 inside the square root. If the 2 goes inside the square root, it's going to turn into a 4. And then we're going to have 4 over 2. And so we're going to end up with a 2 in the top. So that's going to give us square root of 2m omega over h bar. I'll complete this square root. So we have 2m omega over h bar. That's the result of moving the 2 inside. It cancels with one of these 2's in the bottom, and we have an extra 2 in the top. And then we also have this position operator over here. And we can actually divide both sides by this factor and isolate x. So I'll do that on the right. So we're going to have x hat is equal to the reciprocal of this. So we're going to have the square root of h bar on 2m omega. And then we have to multiply by the sum of A dagger and A. Now we could write these guys in any order. We could do A plus A dagger, but I'm choosing to keep it in this order. As we'll see in the expression for momentum, we're going to have some corresponding attributes between these two expressions. So what's happened over here? I've just written the position operator as the sum of A dagger and A, but we just have this constant out the front. So this is the constant of proportionality between these two guys. So we're going to do the same thing for momentum now. Let's have a look at what happens for momentum. For momentum, what I'm going to do is I'm going to subtract this guy from this guy. So I'm going to take A dagger, and I'm going to subtract A. This is the reason for this ordering over here. That's why I'm putting A dagger first, because this is going to give us the nice expression. Okay, so what are we going to get when we subtract these guys? So x and x over here, they're going to have opposing signs. We're going to have x minus x when we subtract, when we do A dagger minus A. So these guys are going to disappear. There's going to be no position. But there will be momentum. So what's going to happen with momentum? Well, we already have a minus sign over here. And when we subtract this, we're going to introduce another minus sign. So we're going to have another minus sign. So we're going to have two copies of this term over here, and there's going to be a minus sign out the front. But we're also going to have this square root term. So it's the same square root term we had in the previous expression. That's m omega over 2h bar, and that is all underneath a square root. And then we're also going to have minus 2i. So we do still have that I over here. That's the imaginary unit I. And we're dividing by m omega. So that's very interesting, isn't it? We have 2 and then m omega over here. And we also have p. We have the momentum operator. So now let's have a look at what we can do over here. Now, we have m omega over 2 inside the square root, and we have 2 over m omega outside the square root. That is the reciprocal of what's inside over here, if we ignore the h bar. So what's going to happen when we put this inside the square root? Well, we're just going to be left with 2 over m omega inside, because we're going to have this squared inside, and one of those terms is going to cancel with this term over here. So I'll write this out in full. We're going to have minus I times the square root of, so we're going to have 2 m omega, and we're going to have a h bar as well. So I'll write this slightly differently. I'll write it as m h bar omega, and at the top, we're going to have a 2. So there's a 2 over here, and in the bottom, we have m h bar omega. And I'll close this square root, and I'll put p over here. And this, we can actually invert. We can divide both sides by this. Have a look at this. We have minus I over here. And if we have minus I, all we have to do is multiply both sides by I, and that's going to cancel this minus I. I just want to be very clear with this square root term over here. All I did is I moved this 2 over m omega to the inside. And that gave us an m omega all squared inside, which canceled with this top term. So that's why we have m omega in the bottom. H bar is still there. 2 went in, and it became 4, and it canceled with this 2 down here, and just left a 2. So that's the same reasoning that we used to put this 2 inside the square root. So we have 2 over m h bar omega. And we also have this minus I. So let's multiply both sides of this equation by I, and let's also get rid of this term by dividing by it, or multiplying by its reciprocal. So that's going to give us momentum is equal to I times the square root of, I'll write this as m h bar omega. The order of these guys doesn't matter. Divided by 2. That's because they are numerical values. So the order doesn't matter. Those guys do satisfy commutativity. These operators do not necessarily satisfy commutativity. Then we have a dagger minus a. So here we have a dagger minus a. That's come from this part over here. So all we've done is we've taken the reciprocal of this square root, and that's put this m h bar omega at the top and the 2 in the bottom. And this minus I has turned to an I. You can think of this as actually the reciprocal, because the multiplicative inverse of I is minus I. When you multiply minus I and I together, you get 1, which is the multiplicative identity. So that is all good. So all we've done is just move this minus I to the other side, and that's turned it into an I. So now we have expressions for position and momentum in terms of the ladder operators, a dagger and a. So you can get position by adding the ladder operators, and you can get momentum by subtracting the ladder operators. The only difference between that simple operation is these constants out the front. Over here we have a real constant, and over here we have an imaginary constant. The imaginary unit I shows up in this relationship. Another important thing that we're going to need before we put this into the Hamiltonian is I'm just going to write the commutation relation for A and A dagger. The order is important. We have to keep the order in mind. So A and A dagger, we take the commutator of A and A dagger. That is defined as A times A dagger minus A dagger times A. So what have we done over here? We've just swapped the order. So here we have A and A dagger, and then we've swapped it, and we have A dagger and then A. And this is the same as 1. So I'm going to prove this in another video in the quantum mechanics playlist. So make sure you check out that video for the proof of this commutation relation. This is analogous to the canonical commutation relation that links position and momentum. So when we take the commutator of position and momentum, we get I h bar. But when we take the commutator of A and A dagger, we get 1. So both of these pairs of operators are non-commuting. Their commutator is non-zero. But here we have 1, and when we take these guys, we just get I h bar. So here it's a little bit of a more simple expression, because we just have 1. So let's have a look at what happens when we substitute these definitions for position and momentum into the Hamiltonian for the quantum harmonic oscillator. So I'll do that underneath. So I'm going to take H, I'm going to write it as the kinetic plus the potential energy. So this is H hat, which is the Hamiltonian operator. And I'm going to write that as the sum of the kinetic energy term, so that's P squared over 2m, and P has a hat because it's an operator. And then we also have 1/2 m omega squared x hat squared. So this is the kinetic energy, and this is the potential energy. You can think of this as analogous to the Hookean potential in classical mechanics. We can also write a K over here. That would be the constant for a spring in classical mechanics, but I've chosen to write it in terms of mass and the angular frequency, because these are far more useful quantities to work with in quantum mechanics, because we're not dealing with a classical mass on a spring. We're dealing with a quantum harmonic oscillator. Okay, so we have this expression for the Hamiltonian. Now I'm going to take these two operators over here. I'm going to write them in terms of the ladder operators. So I'm just going to substitute these relationships into this expression. And what are we going to get? I'll write this over here. So first, we're going to have 1 on 2m. So we have 1 on 2m. And we're also going to get a minus sign. Now, why is that the case? Because we're squaring p squared, but p has an I over here. It's got the imaginary unit. So this I is going to get squared, and it's going to get turned into -1. So I squared is -1, and that explains this. Now, what's going to happen to this term over here? Well, it's going to get squared, so the square root is going to disappear. So we're going to have m h bar omega over 2. And then we're going to have this, which is a dagger minus a all squared. So we're squaring this. And then what we're going to do, we're going to have to take this potential energy term, and I'll combine these guys into m omega squared on 2. So we're going to have m omega squared on 2. And then what are we going to do? Well, we have this, and now we just need the position operator squared. This is the position operator. We're going to take the square of that. So this square root is going to disappear. Then we're going to have h bar over 2m omega. So that's this constant at the front. And now let's take the square of this. So we're going to have a dagger plus a, and that's all squared. So let's have a look at what's going on over here. So we've turned this kinetic energy operator and this potential energy operator into this big mess that involves the ladder operators. So this factor of 1 on 2m has come from the expression for the Hamiltonian. This -1 has come from squaring I. This m h bar omega on 2 has come from squaring this square root. And then we've got this subtraction term from here. And then we have m omega squared on 2. That is the constant that's come from the potential energy term. And when we squared position, we have this term, h bar over 2m omega. The square root has disappeared. And then finally, we're squaring this. I want you to notice something very interesting. Inside the square root over here, what is the difference between these two constants? Over here we have h bar over 2, and we still have h bar over 2. The only difference is m omega appears in the bottom, and m omega appears in the top over here. Now we need that for dimensional consistency. This has units of momentum, and this has units of position. So these guys multiply together, and they match up to guarantee us with the correct units. So that is one way of thinking of this factor at the front. It guarantees we have the correct units for these operators. And now what we can do is, because we have these combinations over here, those combinations are going to neatly cancel with some of the aspects of these constants in the Hamiltonian expression. Have a look at what's going on over here. Here we have an m, and here we have an m. That m is going to cancel. So we're going to be left with h bar omega over 4, because we have 2's down here. We have 2 times 2. So we're going to have h bar omega over 4 in front of this term. And over here we have an m and m. Those guys are going to cancel. Here we have omega squared over omega. One of those omegas is going to disappear. We're just going to be left with h bar omega over 4. So we're going to get a constant that is shared between these guys. So h bar omega over 4 is going to appear in both of those terms. I'll write that underneath over here. So what we're going to get is h bar omega over 4. I'll put some big brackets over here. This is going to have a minus sign, so I'm going to put this one first. So we're going to have a dagger plus A all squared. That's from this potential energy term. And now the kinetic energy term is going to have a minus sign. That's this guy over here. And that's also going to have h bar omega over 4. And we're going to have a dagger minus a, and then we're going to square that and close the bracket. So that is what we got. So this is a lot more condensed. So now what we have to do is expand these guys. So all we've done is we've cancelled all these little constants and factors, and we've grouped out a common factor, which is h bar omega on 4. And then I swapped the order because this guy has a minus sign. So this term that came from the momentum has a minus sign inside, and it has a minus sign outside. And that minus sign outside has come from I squared. So now let's expand all of this out. And we have to be very careful with the order of these operators. So we're still going to have h bar omega over 4. But now let's have a look at what happens over here. So when we square this, we're going to have the square of this operator plus the square of this operator. And then we're going to have cross terms. So I'll write the simple terms first. So we'll have a dagger squared plus normal a squared. I'll put these guys in brackets so we don't mix up the daggers and the squares. So that is just this squared plus this squared. And then we need the cross terms. So the cross terms are going to be a dagger a plus a dagger. And these guys are not equal to each other because these are not commuting operators, as we know by this commutation relation. And we're going to have to use this in a second. We're going to have to use that commutation relation. So that has come from this term over here. So we've just squared the dagger version, and we have the non-dagger version squared, and then we have the mixed terms. These are the cross terms when we multiply. So here the dagger is first, and here the dagger is second. Now we have to subtract this part over here. So what are we going to get? Well, we're going to get some similar terms, but there's going to be some sign differences. So this minus sign at the front is going to distribute inside, and we're going to get minus a dagger squared minus a squared. And now we have to be careful, right? Because these guys are both positive. When you square both of these guys, even when it's negative, when you square it, the minus sign disappears. So we can just distribute that minus sign onto both of these guys. But now we have to be careful because these cross terms are both going to have a minus sign. So when we multiply both of these guys in different orders, there's going to be one minus sign on the inside. And then when we distribute the minus sign from the outside, we're going to have two minus signs. So minus times minus is plus. So both of those cross terms are going to be positive. So I'll write them over here. We're going to have a dagger, a, and then we're going to have a dagger. So it's actually the same combination that we had over here. We have the dagger first. That's just what I've written by convention. And then we have the dagger last. So the order of these two guys when we're multiplying matters. But the order when we're adding does not matter. Because addition is still commutative. But it's just this multiplication, this applying an operator after another operator, that is not commutative. So we have these four terms from this first part, and then we've subtracted off all of these four terms over here. And I'll close the brackets over here. So that is a separate line underneath. Now, what can we cancel? Here we have a dagger squared and a squared, and this also appears over here with a minus sign. Minus a dagger squared and minus a squared. So we can cancel this and this. And over here we have two copies. This minus times a minus has given us a plus, so we have two copies of the same thing. So we can group these guys together, and we can write factors of 2 out the front. And these guys are just going to disappear. They're going to cancel each other out. So what we're going to be left with is h bar omega over 4 times 2 a dagger a plus 2 a dagger. So that's just these guys over here. We have two copies of them, so I have a factor of 2. And I'm making sure to be consistent. I'm putting this dagger first, and then I'm putting the non-dagger a over here. So we can factor this 2 out, and that's going to give us h bar omega over 2 at the front. And then we'll just have left a dagger a plus a dagger. So a dagger a, and then we have a dagger. What can we do with this? Well, now we're going to use the commutation relation in the top right. So this commutation relation actually tells us something interesting. If we have a dagger, I can add this minus sign, this term with the minus sign, to both sides. that's going to get rid of it over here. So I can move this term to the other side. And I can write that in an alternative way. I can write this as a dagger is equal to this term over here, when I move it to the other side, a dagger A plus 1. So we still have the 1 on this side, and all I've done is I've moved this term to the other side. So we have to keep in mind the order. The order is very important, because the order is going to determine when there's a minus sign or a plus sign. So if we have A and then a dagger, then we're going to have this combination. So let's substitute this guy in here. So we have this guy over here. We have a dagger. We can substitute that inside this expression. So I'll write that underneath. That's equal to h bar omega over 2. And then we have a dagger A plus, so now I'm substituting this guy in. We have a dagger A plus 1. So this combination over here is just substituted. This is equal to, I'll write this over here, this guy over here, a dagger A plus 1, that is the same as A times a dagger. So that's just what we had over here. That's this term that I've substituted in. And now we have 2 copies of a dagger A. So we have 2 copies of that. So what we can do now is we can write this slightly differently. I'll continue with green. So we still have h bar omega 2 on the outside. So h bar omega 2. And now we have 2 copies of a dagger A. And we also have 1 over here. So what can we do with this? Well, we can factor out 2. And that's going to give us h bar omega. And then we're going to have a dagger times A plus 1/2. And this is the expression for the Hamiltonian of the quantum harmonic oscillator in terms of the ladder operators. We can also group these guys together. We can write this as the number operator. So this is the number operator here, a dagger A, n hat, that's the number operator. That tells us which energy level we're at. And this can be written as h bar omega times n hat plus 1/2. That's what we've got. We've got n hat plus 1/2. That's the number operator, and these guys are the ladder operators. So all this algebraic mess over here has just told us that this expression for the Hamiltonian in terms of position and momentum is equivalent to this expression in terms of the ladder operators, and that's also equivalent to this expression in terms of the number operator. These 3 forms of the Hamiltonian are all very good descriptions of the harmonic oscillator in quantum mechanics. So we've described the quantum harmonic oscillator in several different ways. So in this video, we started off with the ladder operators, and we started off with this commutation relationship, which was proven in another video. And we used some algebraic manipulations. We got the position and the momentum operator written in terms of the ladder operators. Then we substituted those into this Hamiltonian, which is actually analogous to the classical Hamiltonian for the harmonic oscillator. And then we did some algebraic working. We used this commutation relation, and we got this final expression. We're going to be using this expression and this expression to examine the energy levels of the quantum harmonic oscillator. If you want to watch the other videos in the quantum mechanics playlist, you can find them if you click over here.